one, fight!
How will we win in the fight against COVID-19 and predict the curve's peak and decline? Well, we can use the S.I.R model to find out. The S.I.R model is also known as the Kermick-McKendrick model because it originates from an article written by A.G. McKendrick and W.O. Kermick called A Contribution to the Mathematical Theory of Epidemics. The S.I.R model works like this. We split the population into three categories: those that haven't been infected but are susceptible to the virus, those that are infected by the virus, and those that either recovered or have died due to the virus. Let's look at an example scenario. Let's start with the population. Initially, one person will be infected. Just to plug in some variables, let's say everyone will make contact with two other random people every day. There's a 100% chance of the virus spreading among contacted people, and it only takes 1 day for an infected person to recover and be immune. After the first few days, we see that the number of susceptible people is decreasing, but the number of infected and recovered people is increasing. Let's see what happens after a few more days. Interesting. It appears that the number of infected people peaked and then declined, and eventually the virus can no longer spread. Now let's do the math. We start with three differential equations, which is basically the slope of the lines. One factor in the change in susceptibles over change in time is a constant called beta. Beta is the number of contacts per person per day, and in the stick figure example, beta is 2. Another factor is the fraction of susceptible people times the fraction of infected people. If you have too little either, the virus won't spread quickly. The change in recovered over change in time equals a constant called gamma, which is the rate of recovery, times the fraction of infected people. Lastly, the change in infected over change in time equals the loss of susceptibles minus the gain in recovered. Now that I have my three differential equations, I am able to use algebra to rearrange the equations and solve for how many susceptibles, infected, and recovered people there will be in the future. I can plug in my new numbers and repeatedly do this process, and eventually I can map out what the S.I.R model will look like. There are many factors that make the predictions of the S.I.R models inaccurate, one of which is that the constant beta actually isn't so constant. But in the words of statistician George E.P. Box, all models are wrong, but some are useful, and that holds especially true here. We can use the S.I.R model to show why social distancing works. Our goal is to drain this infected cup faster than we fill it up. There isn't much we can do to change the rate of recovery, but we can change beta by limiting contacts and washing our hands. And if beta is less than gamma, we will beat this virus together. So stay home, stay safe, and save lives. Thanks for watching.